Good day, everyone. This is the last problem type that we're going to look at, and this is probably the one that's most examinable, really. So this is applications four. Uh, Applications four, and this jumps quite ahead. You may remember when we were doing chapter five, I did miss out a problem type, and that's because that problem type needed Maclaurin series. So I'm going to go and look at uh, this problem. It's on page 142, and it's really explains one of the problems that's in 5E that I'm about to. I'll do one of those from 5E, but first of all, I might just run you through this particular example where we're given what dy dx is. We're given that dy dx is equal to x squared plus y squared, such that this differential equation passes through the point x equals to 1, y equals to 0. Yeah, and what we need to do is we need to produce a Taylor polynomial of degree 3 in order to find out a solution to that. And then once we find out that solution to that Taylor polynomial, we need to find y of 1.1. So rather than solve this problem using Euler's method, do you remember when we used Euler's method? Yeah, we used Euler's method to do this. This time we're going to use a Taylor method to approximate this. And this could be a very handy thing and could be something that you could look at for your IAs in the next couple of weeks. So I'll just run through how we do this. So I'll just reduce that down and stick it over there. Okay, so the first thing that we need to do is we know for a Taylor polynomial, we need to find, if you like, actually they've asked us, okay, a Taylor polynomial, and we're given, if you notice, we're given x equals to 1. So this will be a Taylor polynomial around the point x equals to 1. So what I'm going to do, or really x equals to 1, or we call a equal to 1, yeah? So f of 1, we know, equals to 0. Okay, so we've got that there. F of 1, 0. Let's rub that and make that a bit nicer. F of 1 equals to 0. Now, f dash 1, well, in fact, I might even change this and write y of 1, because I want to use y notation in this. I just find it much easier to use rather than f dash notation. I'm going to use y1 equals to 0. And then I'm going to say what dy dx is. Now, I'm going to go y dash of 1, or f dash 1 really, and I'm going to have a look at that. Now, when x equals to 1, y is equal to 0. So my value of y dash, or the gradient of y dx, is going to be 1 squared plus 0 squared, and that equals to 1. Okay, so I've found y dash 1. Now what I need to find is y double dash. Yeah, so I'm going to differentiate this again. So I'll go, so on the left-hand side, if I differentiate dy dx up here, so I'm differentiating dy dx, which is y dash, I end up with y double dash. So if I take the derivative of y dash, I get y double dash. Then what I've got to do is differentiate that, which I'll get 2x. Yeah, and then I've got to implicitly differentiate this. How do I implicitly differentiate y squared? Well, that becomes 2y times by dy dx, which is just y dash. Okay, so now I've got a value for y double dash. So I just need to find y double dash when x equals to 1 and, well, yeah, when x equals, so now I've got x equals to 1, y is equal to 0, and y dash is equal to 1. So I've got this information. So I've got 2 times by 1 plus 2 times by, now y is 0, and y dash is 1. There's y dash there, it's 1. So I end up here with y double dash is equal to 2. Okay, so I think that, yep. So now let's find y triple dash. Let's go. So we'll go y triple dash is going to equal to. Now, let's just go back here. I've got to differentiate this one more time. So if I differentiate the left-hand side, sorry, if I differentiate the left-hand side, I get y triple dash. Now I've got to differentiate this here with respect to x. So if I differentiate 2x here, if I differentiate 2x with respect to x, I just get 2. And then plus. Now, I've got to be careful here. I've got to use the chain rule here. So I've got a y times by y dash. So what I'm going to need to do here is differentiate that bit first. Sorry, not use the chain rule, use the product rule. I need to differentiate this first, 2y times by y dash, and then I've got to differentiate y dash times by 2y. So how do I differentiate 2y with respect to y? Well, you've got to remember, again, we'll have to implicitly do that. That will become 2y dash. Okay, and then I've got to go times by y dash. And then I've got 2y times, now I've got to differentiate y dash here, which becomes y double dash. Okay, so I've just used this bit here, and I'll just circle this so you can see. I've got to actually differentiate that. And I've used the product rule. So there's the derivative of 2y, yeah, and there's my y dash, and here's the derivative of y dash. Okay, and that's what I end up. So let's find now the value of y triple dash 1. So y triple dash with x equals to 1 will be 2 plus 2 times y dash. Y dash over here is 1, so I've got times by 1 plus 2 times by 0, yeah, times by y double dash, which doesn't really come into it, which is 2. And as we can see here, we should end up with 4. Okay, so there we have it. Now we can formulate our Taylor polynomial about y equals to 1. So let's go. So this will be my Taylor polynomial, y, yeah, as a solution to the differential equation. The first one is, if you remember, we've got y of 1 plus y dash 1 times by x, yeah, the x minus 1, all divided by 1 factorial, plus the next one is y double dash 1, x minus 1 squared on 2 factorial, which is 2, plus y triple dash 1, x minus 1 cubed on 3 factorial. So all in all, now we can just substitute in and write ourselves an equation. So we get y equals y1 is, if we go back here, is 0. So f of 1 or y1 is 0. And then the next one, y dash 1 becomes 1 times by x minus 1. So that will just be x minus 1 plus y double dash is 2 down there. So I've got 2 on 2. I'll just write this out though. 2 on 2, so you can see. Those 2's will cancel each other out. Plus y triple dash is 4 on 6. 4 on 6, which will be 2/3. So that will be 2 x minus 3 cubed. Oh, x minus 1, sorry. X minus 1 cubed on 3. And is that right? Yeah, that's right. And of course, we can just cancel out those 2 there. Now, basically, well, there's my answer. Okay, that's my polynomial. Yeah, a Taylor polynomial that represents the solution to this differential equation here. How cool is that? So this is another great method. Rather than using the Euler method or slope fields or whatever, we can use a Taylor polynomial to approximate that differential equation. And of course, we can use that now rather than using the Euler method to approximate the value of y at x equals to 1.1. We just got to substitute in 1.1 in there to actually get the value. So if we want to find y of 1.1, yeah, that's going to equal to 1.1 minus 1 is 0.1. Yeah, so that's that there. And then I've got 1.1 minus 1 will be plus 0.1 all squared, and the last one will be 2/3 times by 0.1 all cubed. And that is our rough solution. And if you plug it into your calculator, you should get the same answer as what they do in the textbook, of course. Voila. Yep. So that's a really good example of a problem type that you could definitely get in an examination. Why? Well, it uses differential equations, solutions to differential equations. It uses the Taylor polynomial, and we also get an approximation. Now, I mean, they could ask you to do using the Euler method. Yeah, you could use the Euler method, and you could actually look at how close the Euler method is to this particular method here, and see what level of accuracy you might have to get for the Euler method. Yeah, what steps you might have to use in the Euler method to get the same sort of accuracy as this. So that could be a nice IA for you to do. So I just got a cup of tea. Let's move on to actually solving a slightly more tricky one from out of the textbook. So let's jump to page, this is question 3. There's a couple here. There's only 4 questions here that you've got to practice. So I'm just going to do one. This is on page 144, by the way, on page 144. And this is problem 3A2. So this is 3A, problem 2. And I've just chosen this one because I actually like the way that it's done. It's written like this. It's 1 plus 2x divided x. Yeah, is equal to x plus 4y squared. Now, solving this one in particular, and this passes through the point x is equal to 0. So this is when x is equal to 0, y is equal to 1/2. So we know that solution to that differential equation passes through that point. This is a problem where if you haven't done your implicit differentiation and you're not really sure on implicit differentiation, you really need to go back and just solve a couple of those problems, because this one particularly, I'm going to solve in situ. I'm not going to solve for divided x. I'm going to basically differentiate the left-hand side and differentiate the right-hand side as is in place. Okay, so that's pretty much, I'll just stick that problem over there. I'll see if I can do that. Okay, and now I'm going to do that. So there's a fair bit of work here. So the first thing I can find is y when x equals to 0, and we know that's equal to 1/2 because that's what that piece of information here tells us. The other thing that we can automatically find is y dash, because we've got 1 plus 2x, yeah, times by y dash equals to x plus 4y squared. So let's actually substitute in those values. Now I know x is 0, y is equal to 1/2, so I've got, really on this side, I've just got 1 plus 0, because x is 0, y dash equals to 0 plus 4 times 1/2 x squared, which is 1/4. So the right-hand side's 1, yeah? Right-hand side's 1 and the left-hand side's 1. So y dash really is just 1 divided by 1, which equals to 1. Okay, good. So I've found y dash. Now I'm going to find y double dash, and I'm just going to jump up here. So this is, how do I find y double dash? Well, what I've got to do is I'm just going to go back here and consider that there. Okay, I'm going to need to apply the product rule to differentiate this. So I'll differentiate that first, multiplied by y dash. Then I'll differentiate y dash multiplied by that, multiplied by 1 plus x squared. Okay, are you ready? I'm just going to do that here. So I'll differentiate 1 plus 2x, which gives me 2, times by y dash. Yeah, and then what I've got to do is plus 1 plus 2x, and then I've got to differentiate y dash. And of course, if you differentiate y dash, you get y double dash. On this side, if I differentiate x, I get 1. And if I differentiate 4x squared, which is this one here, I've got to do that implicitly. That becomes 8y, but then I need to multiply that by dy dx using the chain rule to implicitly differentiate, and I end up with y dash. Now I can solve for y double dash by substituting all of my values in. So I've got basically 2 times 1 from here. Yeah, so I've got 2 times 1 plus 1 plus 0 times by y double dash equals to 1 plus 8 times by a half times by y dash, which is 1. Which is 4, 5, and I subtract 2, so I'll end up with this y double dash equals to, this becomes 4, yeah, plus 1 is 5, minus 2, so I've basically got 1 plus 4 minus 2, all divided by 1, equals to 3. So y double dash is 3. Right, next I've got to do another derivative, because I need to do, this is a third, I need to find a Taylor series of a third degree, so I now need to differentiate that again. So this is actually good practice, and you should do this. So again, if I differentiate 2y dash, that's easy, that just becomes 2y double dash. Now what I've got to do is I've got to apply the chain rule. I've got to differentiate that bit times by that, and then differentiate that bit and times it by that. So that's what I'm going to do. So I go plus, if I differentiate 1 plus 2x, I get 2. Then I times that by y double dash, and then I've got to add that to 1 plus 2x times by y triple dash, and that's where I get my y triple dash. On this side, 1 just goes to 0, and then here I've got to apply the chain rule again. Yeah, I've got an 8y, I have to differentiate that times by that, then I've got to differentiate y dash times by 8y, so I do have to implicitly differentiate this bit as well. Okay, so that will become, ready? So 8y, if I differentiate that, that will become 8 y dash times by y dash plus 8 y double dash. That was a bit tricky, wasn't it? So I differentiate 8y and I get 8y dash times by y dash. Yeah, so that was tricky. Okay, now I can see a couple of things here I can cancel, really. I could cancel out 2y double dash with this to give me 4 there. 4y. Okay, so I might just write another line just to simplify that a little bit. So I end up with 1 plus 2x y triple dash equals to 4y dash y dash plus 8y double dash. Let's substitute in the values here. On the left hand side, again I get 1, so that's just y double dash, y triple dash. That will equal to 1, won't it, because x is 0. So I've got y 1 2 3 equals to 4 times by 1 times by 1 plus 8 times by 0, because don't forget y, oh no, that's not 0, it's a half, isn't it? Okay, so I've got 8 times by, is that what I've got before? Yep, so I've got 8 times by, y is a half, which is 4, sorry, I've got the wrong pen, 8 times by y is a half, times by y double dash, which is 3. Okay, and that gives me with, that's 4, that's 12 plus 4. What have I done wrong there? I've got 4 there, and that's 4, 12 plus another 4 is 16. I should actually get 8 there. I think I need to check and see what I've done there. I just did this before, so I just wondering why I've got 12 there. 12, that's 4. Hang on. I made a mistake there. Yes, I have. Oh my gosh, Mr. Stewart. Oh, Mr. Stewart, what have you done? Let's go back here and rub this off here. I'm sorry, everyone. I need to go back here. You can't cancel out that. I'm going to have to do that again. This is a bit embarrassing, everyone who's watching this. But that's just the way it goes. So let me just go 3. I rushed ahead there. That was 3 there. Let me just rub that off and make that neater. There. Okay, 3. Okay, I'm going to do this again. So if I differentiate this, I get 2y double dash, and you'll see my mistake in a moment. Plus, if I differentiate that bit there, I end up with 2y double dash plus, yeah, and then that's right, equals to 1 plus 8y dash, yeah, plus 8y double dash. Now what I did before, I don't know why I did that for. I cancelled this out with that. Now y dash times y dash is not y double dash. I don't know why I did that for. I just can't do that. So it was just crazy why I did. So let me just work out what this is. So this will be 3 times 2. So let's just plug everything in. 2 times 3 plus 2 times 3. That's 6 and 6 plus 1. Remember that's 0. So 1 times y triple dash. That's a triple dash there. Equals to, now this will be 1 plus 8 times y dash, which will just be 8. Yeah, and then I've got plus 8 times y, which is 0. Okay, so that will cancel out, and I'm left with, now again, that should disappear. So I'm making so many mistakes here. This is really bad. I almost feel like doing the video again, but I'm not going to. Of course, if I differentiate 1 there, you can see here what I've done there. If I differentiate 1 there, that just disappears to 0. Okay, so I've just got 8 plus, and because y is 0, no, y is a half, so I've got 8 times by a half, which is 4 times by y double dash is 3. Well, I'm finally getting there. So on this side, I've got 12, yeah, plus y triple dash equals 2. This will be 8 plus 12, and that will cancel this time, and I'll end up with y triple dash equals to 8, and that's what I wanted to get. So apologies for that little blunder before. Of course, again, that let's just go back and look at what my blunder was. It's probably important to see that. Yeah, y dash times y dash does not equal to y double dash. Yeah, so I couldn't just cancel that out. That was me just rushing ahead and doing that. Right, now I'm ready to write my Taylor polynomial. Okay, so here we go. And this Taylor polynomial is actually a Maclaurin series. Why? Because we're working around x equals to 0. Yeah, so we don't have to do the Taylor, you know, the x minus a bit. Yeah, we don't have to do that because a is 0 in this case, because this is actually a Maclaurin series. Now they might actually say that in the textbook. Now it says find a Taylor polynomial. So in this case, it's not a Taylor polynomial, it's actually a Maclaurin series. So let's write this out. So we've got y, or if you like, you can say f of x. It doesn't really matter in this case. So let's go y of 0 is a half. So we'll write a half here. Yeah. And then we've got plus y dash, which is 1 times x on 1 factorial. So that's just x, isn't it? I'll just rub that out. So I'll just cut straight to the chase. That'll be x. And then y double dash is 3. So that's going to be 3x squared on 2. And then the last one will be 8 divided by 3 factorial. Well, I'll just write it out. That will be 8x cubed on 6. So you could simplify down that to 4 on 3. But just for now, I'll just leave it like that because I'm running out of space. And there is my Taylor polynomial. I'll just quickly check the answers. So that's 3, 5e. I'm pretty sure that's right, but just in case it's not, 5e. Let me look at a half plus x plus 3. Yeah, so that is correct. Okay. Sorry, made a little blunder getting there, but again, that's a great example of how we can use a Taylor polynomial to solve what looks really like a tricky differential equation. Okay, Hope you found this useful. Yeah, please, if you get time, can you then move on and finish the rest of those ones? So I've done, so at least I've got 3A1, yeah, and 3B1 and B2. I'll write that down and send that to you in Teams anyway. Okay, thank you.